You've probably seen a physics demonstration that looks like straight-up magic, right? One of those things that seems to just break the rules of gravity right in front of you. Well, today we are pulling back the curtain on one of the most famous physics magic tricks there is. Let's dive in.
So take a look at this. It's a classic setup. You've got a spinning bicycle wheel, and one end of its axle is just hanging from a string. Now your brain and everything you know about gravity tells you that wheel should immediately flop over and hang straight down. But it doesn't. It just hangs there suspended, slowly turning in a circle. The big question is, how?
Okay, so while it looks like it's defying gravity, what we're actually seeing is this beautiful fundamental principle of physics in action. It's called gyroscopic precession. And trust me, by the end of this, you'll get exactly what's going on. It's not magic, it's just some very, very cool physics.
All right, to crack this puzzle, we really need to understand two key ingredients that come into play the second that wheel starts spinning. It's all about how two different concepts, a special kind of momentum and a twisting force, interact with each other. Let's break them down.
First up is something called angular momentum. Physicists give it the letter L. The easiest way to think about it is just as the stubbornness of a spinning object. See, a spinning wheel doesn't just have speed, it has a direction of spin. Its angular momentum is like an invisible arrow that points right along that axle. And the key thing is, that arrow wants to stay pointing in the exact same direction. It puts up a fight against anything that tries to tilt it. The second ingredient is torque. And really, torque is just a fancy word for a twisting or a turning force. In our wheel on a string setup, gravity is pulling down on the center of that wheel. And because the wheel is only held up at one end, gravity's pull creates this powerful twisting force, a torque, that's constantly trying to tip the whole thing over. It's like an invisible hand pushing down, trying to twist the axle.
So let's put these two ideas together. The wheel is spinning, right? That creates our stubborn angular momentum arrow, L, pointing out along the axle. At the exact same time, gravity is applying that torque, tau, trying to twist it downwards. Now here's the part that messes with your brain. That downward twisting force doesn't actually pull the arrow down. Instead, it pushes the arrow at a right angle. It pushes it sideways.
And this is a really interesting point that clears up a lot of confusion. That sideways push from the torque, it only changes the direction of the angular momentum. It doesn't change how long that arrow is, which means the wheel keeps its spin speed. In physics terms, the torque isn't doing any work, so it's not adding or taking away any energy from the wheel itself. All it's doing is redirecting it.
Okay, so we've met our two key players, the stubborn angular momentum and the sideways pushing torque from gravity. Now let's see how these two, working together, create that bizarre motion and finally answer our question.
The result of that constant sideways push is the motion you're seeing. That slow, circular movement of the wheel's axis, that's what we call precession. So instead of gravity winning the fight and pulling the wheel down, it's forced into this kind of graceful, circular dance. The torque is constantly pushing the angular momentum vector sideways, so the vector just walks around in a circle.
So can we control the speed of this dance? Oh, absolutely. The physics gives us a pretty clear recipe. The faster you spin the wheel, the bigger its angular momentum, its stubbornness, and the slower it will precess. A really fast spin is just harder to push sideways. On the flip side, a heavier wheel or a longer axle arm increases the torque from gravity, and that makes the wheel precess faster.
All right, let's bring it all home and answer that first question. Why doesn't it fall? Here it is in a nutshell. Because the wheel is spinning, it has angular momentum. The downward pull of gravity gets turned into a sideways torque. And that torque just isn't strong enough to break the angular momentum and tip it over. The only thing it can do is nudge its direction, forcing it into that sideways walk we now know is called precession.
And here's a little bonus detail for you. If you ever do this experiment yourself, you might see that when you first let go of the wheel, it kind of wobbles up and down for a second. That little bobbing motion has a name. It's called nutation. It's just a small oscillation that happens right at the beginning. But tiny bits of friction and air resistance make it fade away pretty quick, leaving you with that smooth, steady precession.
Now, this is way more than just a cool classroom trick. This principle of gyroscopic stability is absolutely everywhere, from the toys we had as kids to some of the most advanced tech we use today. Let's take a look at where this stuff shows up in the real world. Ever wonder why it's so much easier to balance on a bike when it's moving fast? Well, part of the answer is gyroscopic precession. The spinning wheels have angular momentum, they resist being tilted, and that helps keep the bike stable and upright. It's the same idea with a tightrope walker's pole. It's not just about a low center of gravity, That long pole is just really resistant to being rotated. Any tipping motion happens way slower, which gives the walker plenty of time to react and stay balanced.
And the applications scale up in some really incredible ways. The very same principle is used by tiny microscopic gyros in your smartphone to figure out which way you're holding it, and in drones to keep them perfectly level in the air. Zoom out to space, and you'll find that satellites use big internal gyros, they're called reaction wheels, to aim telescopes and antennas with pinpoint accuracy. Even huge ships and airplanes rely on super advanced fiber optic gyroscopes for navigation.
Okay, here's one last mind-bending but really fun thing about spin dynamics. It's called the tennis racket theorem. It basically says that any object, like a book or even your phone, is stable if you spin it along its longest axis or its shortest axis. But if you try to spin it along its middle axis, it becomes unstable and will actually flip over midair. Go ahead, carefully try it with a book. It's a real baffling effect that astronauts have a lot of fun with in zero gravity.
So you see, this is so much bigger than just a wheel on a string. The stability that comes from angular momentum is a fundamental organizing principle of our universe. It dictates how planets orbit, how galaxies are shaped, and even the properties of tiny subatomic particles. It really makes you wonder, right? What other invisible forces are out there creating stability and order all around us, just waiting for us to figure them out?